Hello and welcome to Module 4.2. In this video, we're going to look at antenna gain and learn about something called the principle of antenna reciprocity. So in the previous video, we looked at transmitted power and looked at how the signal spreads out through space, and we talked about how the power density decreases as the area of the sphere gets larger as that signal spreads out through space. Now, I mentioned in the previous video that you can imagine the signal like a light bulb and the light spreading through space, and literally that's what it is. It's not light frequency that we can see, but it's in the electromagnetic spectrum, and the energy spreads out through space. However, it doesn't spread out in all directions the same. The GPS satellite, instead of being like a single light bulb in space with the electromagnetic waves coming out in all directions, it's more like a spotlight. So instead of imagining a light bulb, imagine a spotlight just illuminating a spot. And that's what we show here. And that's literally what the energy looks like coming out of the GPS satellite. But for the purposes of analysis, it's useful to think of the energy dissipation as it's dissipating over a sphere. And so we managed to do that by introducing this notion of antenna gain, which is simply defined as the ratio of the entire sphere over the ratio of the illuminated spot. So we pretend that the antenna has this amount of gain, and then from then on we can do the analysis as if the signal was spreading out over the entire sphere. So it's just a little analysis trick that's used in all kinds of budgeting of signal power. So now we're going to actually work out that gain for GPS. So we start with by saying, imagine the satellite as we just showed, and imagine that spot exactly illuminating the Earth and nothing more. And so we show the Earth there, and let's to keep things a little bit simpler, we can take away the Earth for now and then just show that spot. And so that spot is that cap shown there. So we'll have a spherical cap at the edge of the spot beam. And that's indeed what we have. And so now we're going to work out a formula for the antenna gain as a function of the angle of this beam, this angle alpha. And it turns out to be quite a simple formula, as you can see at the bottom, and we'll derive that now. So we start with the area of the sphere, 4 pi r squared, where r is the radius of the sphere. That would be the distance from the satellite to the edge of where that spot touches the Earth. And then the area of the spherical cap, we're going to write in terms of this distance p. So let's just go through what we have here. We have this distance p, which is the slant angle from the middle here to the edge of that cap. H is that distance there. B is this distance here between that line and the satellite. A is the vertical distance there, and alpha is that angle. So now we can just we can just start filling in some values in terms of other values. We've got a right angle triangle here by construction, and so A is, and this angle is also alpha. So A is simply r sine alpha, and B is r cos alpha. And we've got those two terms here. And so what we're trying to do is write everything in terms of alpha. H is simply r minus B. It's this extra term here. And so substituting in B in terms of alpha, we have r into 1 minus cos alpha. And then for P, we just use Pythagoras' theorem on this triangle. And so P here, P squared is A squared plus H squared, so P is the square root of H squared plus A squared, and we can substitute in these previously worked out values for H and A from here, and we get R into the square root of 2 minus 2 cos alpha. So now we've got everything in terms of alpha, and we can go and write out our gain, and we'll just do it up here so you can see how it simplifies so nicely. So we have the gain is the ratio of the entire sphere, 4 pi r squared, over the ratio of the spherical cap, which is pi times p squared. And now we know what p is in terms of alpha. So p squared is this value here, squared. So it's r squared, and the square root sign disappears, and I'm going to take out 2 and write it as 1 minus cos alpha. And so you can see how this simplifies so nicely. The r's cancel, the pi cancels, and 2 goes into 4 twice, and we are left with this elegant result that for any given alpha, the antenna gain is 2 over 1 minus cosine of alpha. So that's a nice result. And so now let's look at some actual values. So we'll bring back the Earth, and for GPS and for the altitude of the GPS satellite above the Earth, if indeed the spot exactly illuminated the Earth and nothing else, then this angle alpha would be 13.9 degrees. However, the GPS satellite doesn't exactly illuminate the Earth. It actually has a slightly wider spot, which we'll draw on this diagram, like this. And so the actual alpha for GPS is 21.3 degrees. And so the signal illuminates the Earth and a little bit more, which is quite convenient for using GPS for other satellites. So for example, if you have a low Earth orbit satellite going around the Earth like this, as it comes around the Earth, it can see the GPS satellites, and so it can make measurements, and this is the genesis of a whole lot of science where we can learn something about the atmosphere as the satellites move through the atmosphere, and they can measure the signals from the GPS satellites on the other side of the Earth. So that's the antenna gain analysis in terms of a signal, a uniform signal across a part of a sphere, just the cap of a sphere. Now we're going to look at a little bit more detail of how GPS antenna gain actually is constructed, and the way it's constructed is not quite uniform over the spot beam. And the reason for that is that the GPS is designed to try and give you the same signal strength if you're standing at this part of the Earth. So if you were standing on the Earth here and observing the satellite on your horizon, or if you were standing on the Earth here and observing that satellite straight overhead, the GPS system is designed so that the received signal strength is about the same. And the way that's achieved is by having the antenna gain along the blue line be 10 dB, or a linear ratio of 10, and the antenna gain along the red line, which is longer, being stronger, 12 dB, or a linear ratio of 17. And then in each of those directions, what we call the effective power that's transmitted is just this 27 watts that we began with up here, multiplied by this gain. And so we pretend in each case that if we're standing at the edge of the red line, that the satellite really was transmitting 460 watts and being distributed over a sphere. And if you were standing at the edge of the blue line, we pretend that the satellite really was transmitting 270 watts. And that's how we do the further analysis. And so with those gains, we can then work out what the received power would be. And the received power is, as we mentioned, we assign the antenna gain, so that's GT for the transmit gain, multiply by the transmit power and divide by the dilution as the signal spreads out through space, and then multiply by the receive antenna gain as GA, which we will do analysis of next. And given all that, we can work out a received power, and if we do that, what we'll find is that the received power for somebody observing the signal on the horizon is minus 128.5 dBm, and for somebody observing it at zenith, straight above them, is also minus 128.5 dBm. And so no matter where you are on Earth, the GPS system is trying to give you the same signal power. Now, what signal power you actually observe is also going to be a function of your receive antenna, and we're going to look at that next. So antennas are always come with a polar gain pattern like this. And so we'll explain what this is. This is a gain pattern for a patch antenna. Now, a patch antenna is something you might have seen if you see a GPS antenna on the roof of a car or maybe on the dashboard of a car. It's usually well, often it's a small patch-like device with some kind of magnet on the bottom. And inside of that, you would see this. There's literally a patch and a small ground plane. And if it's part of a car, then you'd have a large ground plane. And because of this construction, if this antenna transmitted a signal, all the energy goes up in a hemisphere and almost no energy goes down because of that ground plane. And that's what this gain pattern shows us. And so to understand this, let's draw the horizontal plane. And that's what this line is here. So there's the horizontal plane. And that corresponds to this ground plane in this actual antenna. And then up is this way and down is this way, as shown on the slide. And so now if you imagine the transmitted power, all the power going into this antenna gets spread out over this hemisphere and almost nothing over that hemisphere. So we would have a gain of about 2 times. And you remember when we talked about decibels, we said a gain of 2 is 3 dB, and that's exactly what's shown here. You can see there's a 0 dB line there, there's the 10 dB line here, and it's showing us that all the way over this hemisphere, we've got a gain of about 3 dB compared to what we would have if the signal transmitted the same in all directions. And then below, we've got almost nothing. It looks complicated because just the way the antenna is, but if you just go look at a particular value, here it's at the minus 20 dB line, and then even smaller values here. But minus 20 dB means 100 times smaller. So roughly speaking, we have something like 100 to 1,000 times less gain down than we have up. So you can roughly think of it as no signal goes down, all the signals goes up, hence the 3 dB gain. And that's a gain over what you would have if the signal transmitted equally in all directions, which we call isotropic. So it's 3 dB over isotropic, hence 3 dBi. We write it like that. So that's easy to understand about how the signal would transmit. How would it receive a signal? Well, that's where we make use of this nice principle called the principle of reciprocity that says receive gain is equal to transmit gain. And so we don't have to get into the details of why that is true. You just need to know that it is true, and you can think about antenna in terms of how it would transmit, and then you can understand how it will receive. So that's what a patch antenna looks like. Inside, you might be more used to seeing GPS antennas that look like this. Any kind of survey receiver will have an antenna like this. Most of this antenna is ground plane, and inside of this, you'll find a similar patch to that. And so everything we've talked about would be true for an antenna like this as well. And finally, in terms of antenna analysis, you have something known as the effective area of a receive antenna, and that's a function of the wavelength. And so it's simply given by this formula. The effective area is wavelength squared over 4 pi, and where pi is the wavelength of the GPS signal. Just to, if you wanted to work that out, just remember that pi, lambda, the wavelength, times frequency gives you the speed of light. Just a nice trick to remember that is look at the units. The wavelength would be in units. The frequency would be in hertz, which is seconds to the -1. So meters, seconds to the -1, which is the same thing as speed, meters per second. So you make sure you have your formula right. So lambda f equals c, lambda equals c over f, plug in the value, speed of light, the L1 frequency of GPS. This is one of the few things you really have to remember, 1575.42 megahertz, and plug in those values, you see that the wavelength is 19 centimeters, and that gives you the effective area of the GPS antenna. So of the GPS receive antenna. So that sets us up to do the link budget, which we'll do in the next video.